So, welcome everyone. My name is Stefan. I'm professor at Munich University of Applied Sciences. I will talk a little bit about it, what it means. It's a little bit different than typical research institutions, research universities in Germany. And there are some specific challenges if you want to teach computer architecture in a very practical way that I will talk about. So maybe as a background, professionally, I have graduated from Aachen University and Munich University, and I majored in computer engineering, in electrical engineering, which will become more important later. My research interests are in many core, system-on-chip, massively parallels, physical hardware security and verification. That's just a side note. And I've become a professor in March, which is like half a year back, right? And it was really great for me for one particular reason, because on the other hand, I'm also an hobbyist. So I spent the last 10 years on the Open RISC project, for example, which was an open source ISA before RISC-V. When RISC-V started, I immediately started using it too, contributed a little bit, and I'm a contributor and user of many open source hardware projects, like HDL projects and EDA tools around it. So that's the natural fit for me, like it's a good job to have if you're a hobbyist. Some of you may know me from another context, which also plays nice into it. I'm director at the Free and Open Source Silicon Foundation, which is an advocacy group, and we are doing some community building. So I'm really deep into open source silicon. So a little bit of background about what the University of Applied Sciences is, and Munich University of Applied Sciences is the second largest in Germany. We have around 20,000 students in 14 departments. And they are slightly different from what you usually expect as a university. From the characteristics, we primarily do bachelor degrees, which are the largest number of students that we have, and we have some master degrees too. But it's very strongly focused on practical and application-oriented education. So also the research that we do is pretty much application-oriented, and we have very small class sizes. Whenever we have more than 40 students, we start splitting them up in smaller courses. So there's never more than 40 students, so you can do very hands-on and direct interaction with students. We have compulsory industry internship, and this is also the same for professors. Professors have to have at least 5 years experience in industry before joining as a professor there. So that's where I came in, and yeah, probably if you're from the US, comparable is our strategic partner, which is Cal Poly in San Luis Obispo, or the Universities of Applied Sciences in Tampere, in Finland, or in Vienna, Zurich. Those are kind of the references here. So very strongly practical education. My faculty is computer science and mathematics, so I'm originally an electrical engineer, moving a little bit up the stack a little bit, it felt at the beginning. So I'm at the faculty at the lowest level currently. And my first course was kind of the jackpot for me. It was computer architecture, so this is kind of my main topic, computer engineering, computer architecture. I have 4th semester bachelor students, and it's a very classic curriculum. So we start with pipelining basics, so the standard stuff from the textbooks, and we go into how we got to the large IPCs that we have nowadays with branch prediction, superscale, out of order, etc., doing some memory hierarchy, interconnect, and so on. And as I said, it's very practically, so there's a lecture part and there's an equally sized integrated laboratory part where you really spend a lot of time with the students doing hands-on experience and giving them like the first-hand experience of what it actually means, what they're doing. And all this with the cool open source stuff out there, so this was for me like something I really looked forward to for a couple of weeks before I actually started. And I was thinking about how could we do this, and of course I wanted to do it around RISC-V. And so I started developing a little bit, and I was like, really, yeah, this is great, that's why I did it, right? This is the course that I want to teach. But then, just like after a few weeks with the students, I discovered there's a problem. And the problem is that when I think about computer architecture, I think about waveforms and about nice debugging designs and how cool it is and how awesome to do HDL and then dig deep into the problems, understand what's going on. So that's my view on it. And the students that I have, like as I said, as computer science students with a slightly more different focus from what I have in experience. When they hear computer, they think about a gray box that their parents had, probably. And they are purely educated mostly in Java and thinking about UML and so on and so on. And they are just wondering, like, how does it fit now? What can you teach me, right? So there was like a slight mismatch, and it was a challenge for me a little bit. And I just want to talk about it a little bit, how I tackled it. So the lecture is pretty straightforward. So if you design a computer architecture lecture, you just make sure you have 2 books in your library in large numbers, which is the computer organization and design and computer architecture quantitative approach. There's this RISC-V edition, which is very good. Like if you want to teach it, that's probably the best starter. The other one is more like if you go into the details later. So the lecture is pretty easy, and you can just design it in a couple of weeks probably. But then I thought about the laboratory, like the practical assignments. And I structured it roughly in 3 parts. I started with a little bit of RISC-V Basics, and I want to talk about it in a little bit more details now. Where we start with a refresher in computer systems. The students probably had some very basic course already in this area. Then we go into the RISC-V instruction set in assembly, using the standard open source tools that you would use, like Spike, RISC-V8, and the Venus simulator. And then we go to the actual computer architecture part and start with the DLX Pipeline. There's a nice simulator tool out there. We talk about other simulators. This is something I found very important, that the students understand what they are doing, what it means running simulators, emulators, what they're actually simulating, and which level of abstraction we are talking about. So we have an extra week about this. And then we do a little bit of RTL simulation of popular open source CPUs, starting with the IBEX core, the STR1 from Syntacore, then Rocket, Ariane, and Boom. So that's like probably the landscape of RISC-V cores. And in the end, we just go to the FPGA and run a little bit of FPGA fun, booting Linux, like much faster than running simulations before. So that was my idea, and I started with it, and I just want to talk a little bit how I structured it, and especially what I created as tools along the way. So the RISC-V basic stuff is pretty straightforward. What you would do, like you would refresh the assembly skills. RISC-V is very nice in this respect because it's a very clean and simple ISA. We start writing small programs. The idea is that you're refreshing calling convention. Essentially, they are learning it again because they forgot everything. So you're talking about calling conventions, etc., and run those things, and they get a better understanding about what it means talking to a machine, right? And for this, we use this Venus simulator, which is a very nice tool because it runs in the browser, right? It's JavaScript. It's fully functional, like there's no timing, etc. But it's very useful for them for debugging, stepping, and so on. And I found it very useful. And from there, we took it just moving away from this poor functional view up to the first pipeline, right? Starting with the DLX pipeline. And we are teaching them the basics. Yeah? So this is how a pipeline looks like. It has 5 stages, talking about everything. And there I used this RIPE simulator, which I can also warmly recommend to everyone. It's a very nice project, which is done by a student from Denmark, who's putting in a lot of work there. And you could see like how the signals change, how the multiplexers behave, and how you fetch your operands from the register file, etc., etc. And then you can just step through it, and they can see hazards, they can understand your hazards better. And there's like multiple assignments in this direction that we solved then. And then once we are there, the idea was like, now we can do the real computer architecture, and we have real processor cores. And this is really cool because you don't rely on simulators or just running on hardware that you can't really get deeper insights in. And so I did the step going away from these visual simulators that help students understand it better to actual simulators. And started with RV8, so they understand different modes, like what user mode emulation means, and what levels of abstractions are, and how they work, and why you would choose one or the other. And then in the end, we did like an RTL simulation of this Syntacore SCR1, which is a very nicely written and straightforward 2 to 4 stage pipeline processor core. And I prepared everything for the students. They just had to run a simulation, open GTK wave, open the configuration file, and then they could see like how instructions travel through the pipeline and how they are worked on. And like frustration was very high for those students. It was the first time they got in touch with this level of abstraction. And it was really clear to me that we can't go on this layer that I prefer usually, but instead I wanted some more abstract way of interfacing more complex cores. And so the goal was to give them the understanding of the concepts of computer architecture in a way that they can easily handle it and get the insights. And I don't want them to handle waveforms and navigating them. It's not very productive, right? If you have 90 minutes of a lab, you want to get stuff done, right? But I want to use real processor cores. I don't want to use Gem5 or whatever simulator. I want them to understand this is built as a chip somewhere and you can use it simulated, right? So I'm still stuck on very later a little bit, but it's really nice. It's easy to give to the people, and all the cores that I have fortunately already had the test benches, etc. ready. So I just started extending a little bit, and I want to talk about it. And what you can find, for example, is for the Boom processor, this Berkeley out-of-order machine, they have, so they can produce the file format of a microarchitecture trace, which can be consumed by the Gem5 out-of-order pipeline viewer, which probably you saw before. And this is something I wanted, right? This looks like I want that, but I want more. I don't want only the pipeline and see how instructions traverse it. I want students to have the capability to see how the branch predictor behaves, how the fill state of reservation stations is, etc. And that's how I came up with the idea of this pipeline viewer, which is a re-implementation of this basic pipeline viewer, but plus a lot more features that I want to talk about shortly. So it's a Python module. You can just install it with pip install pipeline viewer, and then you can start. As I said, it's a re-implementation of the basic pipeline viewer, but with extra modes. How it works is that we have extensions of all the core simulation environments, so they all have kind of the test benches, and I added a lot of DPI magic into it to just trace the microarchitecture state, try to trace how instructions traverse the pipeline, have the life cycle covered, and then dump it to a file or to some other trace format that I will talk about. So for example, if you look at this Ariane core from ETH Zurich, 64-bit core, I take the test bench, and then I just do minimal extensions. In the beginning, it's useful to have some kind of ID tagging so that you know, next to each instruction that's traversing your processor, you understand which ID it had when you fetch it from memory. But this may become obsolete, and I do it for most of the course over time. Once you better understand the microarchitectural behavior, you can replace and actually track it in your DPI module. And this is what you add then. It's like a microarchitectural tracer module in DPI. It observes the state of the microarchitecture and then creates a trace file. And this trace file is preferably in a common trace format, which is a binary format, which is very dense, easy to generate and handle, or you could use text files, which are kind of similar to what the Gem5 pipeline viewer uses. Yeah, and then you can just read it with the pipeline viewer and see what the core does. And for example, I have one assignment where they have to observe the instructions in the pipeline, and then they have to determine the IPC. And for that, they can run it. So they run a simulation, and it supports different modes. So you could use the debug infrastructure around it, etc., and just filter by user mode, for example. So this is what we see here. You can see how the instructions traverse the pipeline. So you see the life cycle over time. You can see how it's fetched, decoded, issued, executed, written back, and retired. And you can see the color coding for better readability, and you can see how it got stalled in different stages because it couldn't progress. Along with it, you get the total number of retired instructions, which is handy for them to calculate IPCs later, together with the duration. For each instruction, you have duration. You have some that don't have an end time. Those are the ones that got flushed during processing, mostly because of branches, obviously. Together with the duration and the total retired instructions, they could start playing around, making assembler optimizations towards increasing the IPC. Plus, you get the program counter and disassembly, which is for them the link to what we did in the Venus simulator. So then we have another assignment around the branch predictor. This is what I said, I wanted more than just the instructions in the pipeline. I wanted all microarchitectural information that I need for my teaching. So the assignment was kind of comparing the expected behavior to what we had in the lecture, and like the impact of different sizes of the branch history table, for example. And you could like configure it in a way that you get rid of most of the information, but instead add the information of the branch predictor. So this is what you can see here. You can see for each branch if it was taken, what the prediction was, and how the branch history table was updated. And for them, that's the direct link to what we learn in lecture, and an easy way to apply what we've learned. And in my opinion, I think this is like a more accessible way of teaching computer architecture than waveforms or just pure Gem5 high-level simulations. What is work in progress is the FPGA integration. The problem was that the semester was over when I got to it. I spent a lot of time like ramping stuff up. But the idea is that we implement a course in FPGA and we add the microarchitecture trace there too. As I said, I ran out of time, so this will be added in spring 2020. And it's kind of similar setup. You just have the core, but instead you need a synthesizable microarchitecture tracer, which in most cases doesn't mean much. Like it's just a couple of gates. And then we use the infrastructure of OpenSOC debug, which already has at hand the capabilities of transferring traces to the outside world. And then we can store them directly in this common trace format files and use the same flow as we did before for running like larger, like longer system runs on the FPGA, and the students can see it in action. As a short outlook at the end, there's another course I'm teaching this semester. Actually, it's the first semester bachelor course in computer system fundamentals. And of course, I want to change this to RISC-V. Currently, it's MMIX and the virtual motherboard. I don't know who of you is familiar with MMIX. It's by Donald Knuth. I want to switch to RISC-V, and my plan is to extend Venus, which I find still like a very handy simulator, and for example, extend it with I/O visualization. Yeah, so the idea is that there's like some kind of configurable infrastructure where I could add like LEDs or I don't know, like I/O or like a small simulated screen or something like that, and the students get the access from the assembly to those and can run more interesting tasks. Like for them, in the first semester, it has to be more like gamification focused and less computer architecture focused for them to get a better understanding about how computer works. So this will happen next summer. What I also want to do is benchmarking with MBench, which I think gives them like an early and better understanding about what the differences are between different implementations and so on. This then not in the Venus simulator, but probably on FPGA pre-synthesized images. So summarized, I was very curious and very ambitious to do computer architecture teaching with real processor cores, but without waveforms. It's pretty much accessible to non-EE students. No need to touch HDL or waveforms. I think I built a pretty reusable infrastructure. There's some work in progress stuff here and there where I'm just like reiterating. But even the FPGA stuff is pretty much nicely progressing, and I will have it ready for the next spring term. The course that I currently work on is the IBEX core from Low Risk. There's the Synta core SCR1, the ETH Ariane core, and the Berkeley out-of-order machine. Those are the cores that I focus on because they pretty much cover the whole design space. Yeah, I will improve this laboratory curriculum. You can find it online. There's a GitHub repository which is slowly populated by me, which includes like runnable demos of what I'm doing. I probably will add the assignments over time. Currently they're in German, so I have to translate them, etc. But you can find more there, and I'm happy if you get in touch. Just drop me an email, speak to me at the party tonight, send me a tweet, whatever you like. Thank you very much. We have 45 seconds for a question. The question is if I do multi-core too. Yeah, so the idea is, so like the curriculum actually covers it in the lecture, but so far I don't cover it in simulation.